Welcome, data professionals. Today we are exploring a core function for AI and semantic search in Snowflake, vector cosine similarity. Let's get started and learn how to leverage vector geometry for advanced data retrieval. Let's begin by defining what vector cosine similarity actually is. In modern AI, text is converted into multi-dimensional arrays of numbers called vectors. The vector cosine similarity function computes the similarity between two of these vectors. But how does it do this? It looks purely at the angle between the two vectors in that multi-dimensional space, while completely ignoring their magnitude or length. Why is this so revolutionary? Because semantically similar text yields vectors that point in the same general direction. This means a short user query and a massive, detailed document can point in the exact same direction and be matched perfectly. This overcomes the limitations of traditional keyword matching, allowing your database to understand true semantic intent. Take a look at this flowchart, which illustrates the basic data transformation. On the left, we start with two separate pieces of unstructured text. Both are processed by an embedding model to generate vector A and vector B. These two arrays of floating point numbers are then fed directly into the vector cosine similarity function in the center. The engine mathematically compares their angles and outputs a semantic angle score on the right, instantly quantifying how closely related the two text concepts are. To use this function effectively, you must understand the mathematical boundaries it operates within. The cosine similarity is always expressed as a float value in the interval of -1 to 1. What do these numbers mean for your data? If two concepts are perfectly identical, their vectors point in the exact same direction, yielding a cosine similarity of exactly 1. If two concepts are completely unrelated, their vectors are orthogonal or perpendicular, resulting in a similarity of 0. If they are diametrically opposite in meaning, the similarity is -1. Diving a bit deeper into the math, the engine calculates this by taking the inner product of the vectors and dividing it by the product of their lengths. This normalization step is what strips away the text length and leaves only the pure semantic angle. This diagram provides a quick visual reference for interpreting your similarity scores. Starting from the top, the cosine similarity score branches into three critical thresholds. On the left, a score of 1.0 indicates identical meaning the vectors are perfectly aligned. In the center, a score of 0.0 means the vectors are orthogonal, representing completely unrelated topics. On the right, a score of -1.0 means the vectors point in opposite directions, representing opposing concepts. In most business use cases, you will be filtering for scores closest to 1.0. Now let's examine the syntax required to execute this in your SQL queries. You invoke the function by calling vector cosine similarity and passing in exactly two arguments. It is crucial that both of these arguments are already formatted as the Snowflake vector data type. If you try to pass raw JSON arrays or text strings directly into this function, it will fail. You must first embed your raw text using a function like embedText768. Once processed, the function returns a simple float value. As a deep dive constraint, remember that you cannot compare a 768-dimension vector with a 1024-dimension vector. Both inputs must exist in the exact same dimensional space for the geometric calculation to successfully execute. This flow diagram outlines the strict input and output contract of the function. We have vector 1 and vector 2 entering the function block. Notice that both explicitly require the vector data type. They feed into the vector cosine similarity engine, which performs the angle calculation. The engine then outputs the final result, which is always a standard float data type. This simple float output makes it incredibly easy to use in standard SQL order by or where clauses. As senior architects, we must understand the hardware realities of the tools we use. Vector similarity search involves massive amounts of floating point arithmetic. To perform these calculations across billions of dimensions in milliseconds, Snowflake optimizes the vector functions at the system level. However, this optimization can slightly reduce floating point precision. Specifically, the vector cosine similarity functions results have a documented margin of error up to 1 × 10 to the power of -4. This means the score might fluctuate slightly at the 4th decimal place. Why does this matter? Because you should never build application logic that expects a mathematically perfect match out to 10 decimal places. Instead, use these scores for relative ranking, finding the top 5 closest matches rather than demanding an exact mathematical equality. Let's visualize this architectural trade-off. We push a massive vector array into the database's hardware optimization layer. This specialized layer is designed to process geometric math incredibly fast, leading directly to high-speed query execution. However, as indicated by the dashed line, this speed introduces a minor precision trade-off. This results in a defined margin of error of 1 times 10 to the power of -4. Understanding this flow ensures you design robust, fault-tolerant similarity thresholds in your downstream applications. Let's dive into query optimization, which is arguably the most important lesson today. How you construct your SQL dictates your performance and costs. The golden rule is this: generally, the call to the vector similarity function should appear in the select clause, not in the where clause. Why? Because if you place vector math in a where condition across a billion-row table, you force the compute engine to execute heavy floating-point geometry on every single row before filtering. Instead, use standard SQL criteria like date ranges or category IDs in your where clause to drastically reduce the dataset first. Then, calculate the similarity only for the remaining rows in the select clause. You can define a column alias for the result in the select clause and use that alias to order or limit your final output. Look at this highly optimized query execution plan. We start with 1 billion rows at the top. Instead of doing math immediately, we hit the where clause filter, which cheaply removes old records, passing only 10,000 rows forward. Only then do we hit the select clause containing our vector cosine similarity function. The expensive vector math is calculated on just this tiny subset. Finally, we order by the similarity descending and limit to 5. This pipeline executes in milliseconds instead of minutes. As enterprise leaders, we must practice strong FinOps. You need to clearly distinguish between AI generation costs and vector search costs. When you initially convert your text into vectors using a function like embed text 768, you incur a compute cost based on the number of tokens processed. However, once those vectors are safely stored in your tables, running the vector cosine similarity function during a user search does not incur any token-based costs. The similarity math simply consumes standard virtual warehouse compute, just like a standard SQL join or aggregation. Therefore, the absolute best practice is to compute your embeddings exactly once at ingestion. By storing the vectors permanently, your application can execute millions of real-time similarity searches using only predictable, standard warehouse compute, protecting your AI budgets. This diagram breaks down the cost separation. On the left, converting raw text via the embed text function incurs a one-time token cost, highlighted in red. The resulting data is saved in the vector column. Later, when a search query arrives, it triggers the vector cosine similarity engine against that stored data. As highlighted in green, this path incurs 0 token cost. It solely utilizes standard warehouse compute, making high-volume read queries incredibly cost-effective. Let's apply this to a powerful real-world scenario, Retrieval Augmented Generation, or RAG, for a customer support help desk. When a new support case is logged, your team benefits massively from finding similar cases that have already been resolved. First, you add a vector column to your historical issues table and embed all past issue text. Now, a frustrated user submits a poorly worded ticket. Your application embeds this new query on the fly. Next, it runs vector cosine similarity against the historical table, ordering descending by similarity and limiting to the top 5. Finally, it passes the text of those top 5 resolved issues to an LLM like Mistral or Claude. Because you provided perfectly retrieved historical context, the LLM generates a highly accurate, grounded resolution for the customer instantly. Let's trace the RAG execution flow. The user submits a new ticket complaining about an app crash. The database instantly embeds this query and calculates the cosine similarity against all stored historical vectors. It grabs the best matches and passes those top 3 historically resolved tickets directly into the Cortex AI large language model. The LLM reads the proven internal documentation and synthesizes a perfect step-by-step fix back to the user, completely automating Tier 1 support. To summarize, the vector cosine similarity function is your primary engine for semantic search. By computing the angle between 2 vectors and ignoring their magnitude, it finds true semantic relationships regardless of text length. Remember to architect your queries intelligently. Filter out irrelevant rows in your where clause first to minimize the math the engine must perform in the select clause. Keep your economics in check by pre-calculating your embeddings, ensuring that your high-volume similarity searches only consume standard warehouse compute with 0 token fees. You now have the skills to build highly accurate, hallucination-free RAG applications entirely within Snowflake's secure perimeter. To master these concepts, invite learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. This final mind map summarizes our entire module. At the core is cosine similarity. Branching out, we recall the core math, which is angle-based and bounded between -1 and 1. We must apply optimization by placing the function in the select clause after pre-filtering. The economics are highly favorable, utilizing standard compute with zero token costs for the search itself. All of this enables our ultimate use cases, building powerful semantic search engines and RAG chatbots. See you at QuickTechie.